Hello maths fans, Dr Tom Crawford here at the University of Oxford, and today we're looking at how to calculate the determinant of a matrix. So far in the linear algebra series, we've looked at solving systems of linear equations and calculating the inverse of a matrix. Now what both of these topics have in common is the use of elementary row operations, or EROs. When looking at determinants, we can once again use EROs to simplify our calculations, and that is exactly what we'll be doing in part 2 of this video. In part 1, we'll look at the theory behind the general formulae for determinants of a 2x2 and 3x3 matrix. As usual, I'll be going through some worked examples to help to build your understanding. And don't forget, you can sign up for a 30-day free trial with ProPrep, where you can access many more examples, each with a video solution. ProPrep is an online resource that provides customized tutorials for students looking to improve their skills in STEM-based subjects. All of the ProPrep exercises are available via the links in the video description, and you can access the videos by signing up for a free trial using the link below. For our first example, let's look at a general 2x2 matrix, so something of the form A, B, C, D, where these entries, of course, could be any number. Now, we define the determinant of this 2x2 matrix to be A times D minus B times C. So what we're doing is the top left multiplied by the bottom right, and then you subtract the top right multiplied by the bottom left. So if you just remember, for this matrix ABCD, the determinant is equal to AD minus BC. Now, to understand exactly why this is how we calculate a 2x2 determinant is quite advanced. So I teach this in the Linear Algebra 2 course here at Oxford to my first year students, but this is taught in their second term. However, I'll go through the basic idea just so you have a flavour of where this comes from. We start by considering a general function d, and this is of course going to be our determinant. And we want this function to map from the n by n matrices, and just to make it easier here, we'll just consider real entries. So it's going to map from a matrix to give us a real number. So here we start with a matrix and we output this scalar AD minus BC. So this is clearly mapping from matrices to the real numbers, where here n is 2. Now we want to look for a general function of this form such that it satisfies 3 specific properties. So the first property that it needs to have is that if we swap the order of 2 rows, so swapping 2 rows in our matrix should actually give the negative of the original answer. So swapping 2 rows gives the negative of the original answer for the determinant. So that's going to be our first property that we want this general function d, our determinant, to satisfy. Now the second property that we want it to satisfy is to say that multiplying by a scalar, or multiplying a row by a scalar, by lambda, representing our scalar, then that multiplies the answer by the same scalar. So notice we're not multiplying the whole matrix by this scalar, just multiplying a single row gives an answer that has lambda in front of it. So multiplying a row by lambda gives original determinant times lambda. And then the third and final property is that if we have 2 rows of the same, then the determinant should be 0. So with these 3 specific properties, and I'm aware this is quite abstract and quite general at this stage, but if we define a function d from the matrices to the real numbers, such that these 3 properties are satisfied, then you can show, it's a clever proof, you can show that the determinant is in fact unique. So given these three properties, you can show that this function d, which is going to be the determinant function, is unique. Now where this is really helpful is as follows. If we can write down a candidate for this function, so if we can write down a function d, which we'll call the det, such that it maps from a square matrix to a scalar, to a real number, if we can write something down such that properties 1, 2 and 3 are all satisfied, then because it's possible to show that anything satisfying this is unique, there is only one such function doing this, if we can come up with that, maybe try something like this, then this must be the determinant. Because we're saying all determinants satisfy these three rules, however, that allows us to show that the determinant itself is a unique function. These properties define a unique function. So if we can then write down a candidate to be that function and show that it satisfies these three rules, then we have in fact found the unique determinant, because only one exists. So uniqueness here is really, really powerful in allowing us to show that this is indeed the determinant function for a 2 by 2 matrix. So to show that, all we have to do is show that this function satisfies these three rules. Now just as an aside, some of you, if you've watched the earlier videos in the series, may be looking at these three properties and thinking that they look quite familiar. And you'd be right, they're very similar to elementary row operations. We're talking about multiplying rows by scalars, we're talking about repeated rows, which we saw in the systems of linear equations video, and we're also talking about swapping two rows. So we will see in part 2 of this video exactly why these properties are so important, because we can use EROs to simplify our calculations and make calculating determinants much easier. But more on that in part 2. So now let's check that our function, or our definition of a 2 by 2 determinant, satisfies these three rules. Because remember, if it does, then we have the unique determinant for a 2 by 2 matrix. So, the first property says if we swap two rows, we should get the negative of the original determinant. So, the original determinant of ABCD, this matrix, is AD minus BC. That's how we're defining it. So now if I swap two rows, so that means putting C and D on top, and then A and B on the bottom. So we only have two rows, so I just have to swap those two. And now if we use our same definition, so we take top left times bottom right, so we can say here the determinant of this is CB minus DA. But this is very similar to the original determinant, and in fact it's exactly what we want. Because if I take a minus out the front, then I can write that as AD. DA is the same as AD when you're working with scalars, real numbers. And then we've got minus BC. So the answer here, having swapped two rows, is indeed the negative of the original determinant. So this is satisfied. Property 1 is satisfied by this definition for a 2 by 2 matrix determinant. Now for the second property, we need to multiply a single row in our original matrix, and we should get the same scalar, we'll call it lambda, multiplying our determinant. So let's try that. So let's just multiply the top row, and we'll have lambda A, lambda B, and then we've got C, and then we've got D. So now we calculate the determinant in the same way. Top left times bottom right, so that's lambda A, D, minus lambda B, C. So that's our det. But of course we can factor out that lambda, and it's lambda AD minus BC. So again, property 2 is satisfied. We multiply a single row in our matrix by lambda, and it multiplies the whole determinant by the same scalar, as we can see here. For the third property, we need a repeated row in our matrix. So let's just write out 2 times the first row, so AB and AB. Then if we calculate the determinant, again, it's top left times bottom right, so that's AB minus BA. But once again, A and B are scalars, they're real numbers, so this is just 0. So property 3 is also satisfied. So in summary, what all of this means is that the function we have here, AD minus BC, i.e. top left times bottom right minus top right times bottom left, this function for a 2 by 2 determinant satisfies all 3 properties, so it satisfies everything required to be a determinant function, and then we just appeal to uniqueness. So because we can show any function satisfying these 3 things is unique, what we have written down here satisfies these 3 things, therefore we have found the one and only way of calculating a 2 by 2 determinant. Don't worry if this all seems a little abstract. There are plenty of practice exercises courtesy of ProPrep which you can access via the links in the video description. There are also answer sheets available so you can check your work, and if you sign up for the 30-day free trial you can watch full video solutions. For a 3 by 3 matrix, the idea is basically the same, except now we have several 2 by 2 matrices that we need to calculate the determinants of, and then combine them in the correct way. This is how it works. So let's start with a general matrix of A, B, C, D, E, F, G, H, I. So these just represent 9 different scalars, 9 different real numbers. This is not necessarily E, as in Euler's number, and this is definitely not the square root of minus 1. These are just 9 variables representing the 9 entries of our matrix. So we start by taking the first entry, A, so we can say the determinant of this is equal to. We take the first entry, A, and then we cross off the other entries in that column, the first column, and in that first row. So I like to draw these lines in so I can keep track of what I'm doing. Because we cross off these rows and this column, and then we calculate the 2 by 2 determinant of what's left. So here we're left with the 2 by 2, which has E, F, H, and I. Now that's our first 2 by 2 that we've calculated as part of the larger calculation. So next we go to this entry here, so B. So we then also have B, and we want to multiply by the remaining 2 by 2 determinant. So for this one, we cross off this row and the first column. So you have to think a little bit more about what 4 entries remain, but it's going to be D, G, F, and I. Because again, we cross off the first row and the column that that entry is in, so here the second column. So we're left with a 2 by 2, which is D, F, G, I. So D, F, G, I. And then finally, we go to the third entry here, so we cross this column off, we cross off the same top row, and what we're going to be left with now is going to be this box here, this lower left corner. They are the 4 entries remaining, so we have C times D, E, G, H. Now we have all of these pieces, the trick is to now combine them in the correct way. And in order to do this, we need to know something called the coefficient matrix. So the coefficient matrix looks like the following. We have a plus, minus, plus, then we go back to a minus, plus, minus, and then back to a plus, minus, plus. So this is our coefficient matrix. And what this tells us is whether to add or subtract these terms in our 3 by 3 determinant. So it works as follows. We have got our first entry here, A, and the entry here is a plus, so this is a plus. Then we went to the second entry here, we went to B, which is this one here, which is a minus, so we subtract that one. And then again for the third entry, we had C, which is again a plus. So we add this one. So expanding by the first row, as we've done here, we have A times the remaining 2 by 2 determinant minus B times the remaining 2 by 2 determinant and plus C times the remaining 2 by 2 determinant. Now, of course, we can expand these out and get the full final answer, so let's do that. Using our definition of the 2 by 2 determinant, which we've just shown is the unique definition for a determinant, we just simply do top left times bottom right minus the other one. So we're going to get here A times EI minus FH. Then we have minus B times this 2 by 2. So minus B times DI. And then we're going to subtract FG. And finally, we add on the third one. So C, and then it's multiplied by that 2 by 2, which is DH minus EG. Now at this stage, there are two important points that I would like to raise. The first one is, given this definition of the determinant as written here, what you can do is go back to our three determinant properties and you want to check that using this definition, this formula will satisfy all of those three properties, so therefore this function is a determinant function for a 3 by 3 matrix, and we can then appeal to uniqueness just as we did before to say it's not just a determinant function, it is the determinant function, because the uniqueness says there is one and only one such function. So I do recommend, as an exercise to help improve your understanding, taking this function as our definition of a 3 by 3 determinant and convince yourself that it does indeed satisfy those three properties that we looked at before. Therefore, this is the one and only determinant for a 3 by 3 matrix. Now, the second point I'd like to discuss here is how we calculated this particular determinant. And what I mean by that is when I was doing the expansion to get the determinants here, I decided to expand in the first row. Now, you don't have to do this. You are in fact free to expand in the first row, the second row, or the third row. Remembering that as you expand, you move through the columns, and each time you pick an entry, just like we did here with A, you cross off that column and that row, and you calculate the remaining 2 by 2. So you can do this for any of the three rows, and in fact you can do this for any of the three columns. So again, you could expand down this first column, and then you would do A and get the same thing, you'd get D, and you'd get that 2 by 2, B, C, H, I, and then you'd get the third one times G. So you're free to expand in any row or any column. And this is actually a really helpful technique depending on the structure of your matrix. But remember, depending on where you expand, you still have to use the coefficient matrix to get the correct signs in front of those three pieces you have in terms of the 2 by 2 determinants. So for example, if you expand in the second row, then you have D with a negative, then you add E times the remaining 2 by 2, and then you subtract F. So this coefficient matrix is really important, not only in helping you to remember how to expand by the first row, but if you decide to expand by a different row or in fact a column, you still need to take the correct coefficient from this matrix. Let's finish by doing an example to see how all of this works in practice. So we're going to consider the following 3 by 3 matrix. So we'll have 1, 2, 1, minus 5, 10, 1, and 2, 0, minus 1. So a standard 3 by 3 matrix, all with real entries. So first, let's expand using the first row, so this will follow that general formula that we just looked at. So, the determinant is equal to, and this is our first row expansion. Okay, so remember how to do this. We go 1, and it has a plus from our coefficient matrix. So we cross off these and we cross off those. So it's 1 times the remaining 2 by 2 determinant, which is 10, 1, 0, minus 1. 10, 1, 0, minus 1. Now, I do remember what goes next, but let's just check. So the coefficient matrix, always a good idea to write this out in my opinion, and we'll certainly need it later. So this is plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, so the next one, the 2, the next element in our first row, that has a minus. So it's this minus 2, and then the 2 by 2 determinant that we're left with, crossing those off now, is going to be minus 5, 1, 2, and minus 1. So minus 5, 1, 2, and minus 1. And then the third and final term, so that's now a plus, and we have 1, so we cross off this one and the top, and we're left with these elements. So it's going to now be plus 1, and that's multiplied by this 2 by 2, minus 5, 10, minus 5, 10, 2, 0. Okay, so we now expand out the 2 by 2 determinants. We've got 1 multiplied by, top left, bottom right, minus 10, minus 0. So that's minus 10 in total. Then we have minus 2 times the 2 by 2. So minus 5 times minus 1 is 5, minus 2, so that gives you 3 for that 2 by 2 determinant. And then we've got plus 1 multiplied by that determinant, so minus 5 times 0 is 0, minus 20. So it's plus 1 lot of minus 20. So putting this all together, we've got minus 10, minus another 6, minus 20, so that equals minus 36. So, the determinant of this matrix, this 3 by 3 matrix, using the general formula and expanding in row 1, gives us minus 36. Now remember, I said that you can in fact expand via any row or any column. So looking at our original matrix, where do you think we might want to expand? We have a 0 entry here. Now a 0 entry is going to be really helpful if we have that in our row or in our column. Because when we expand, for example, if we do the third row, which is what we're going to do, when you do the third row, that second group term, that second term multiplied by a 2 by 2, it's 0 times the 2 by 2. So we don't actually need to calculate the 2 by 2 because it's going to be multiplied by 0 and therefore always give us 0. So expanding here, expanding in the third row, is actually going to save us some work. So if I had really thought about the best approach to tackle this question, it's always going to be expand in the row or column that has the most zeros. So let's now do that expansion in the third row. So, the third row expansion the determinant is equal to, we take our first entry, the 2, and we cross off like that. So we get, and it's a plus from our coefficient matrix, so it's 2 times what's left, which is 2, 1, 10, 1. 2, 1, 10, 1. Then we've got 0, so minus 0 times a 2 by 2. But it doesn't actually matter what that 2 by 2 determinant is because it's being multiplied by 0, so we get 0. So we have nothing for that next term. And then the final term is, again, it's a plus, and we've got a minus 1. So plus minus 1 gives us a minus times the 2 by 2 that's left, which is going to be this section, top left section up here. So minus the determinant of 1, 2, minus 5, 10. So you can already see that this looks a lot simpler than what we had at the top of the board because we only have 2 lots of 2 by 2 determinants to calculate compared to 3. And this is how this clever choice of where to expand where we have those zeros can actually be really helpful. So, doing these expansions, we have 2 times, the determinant is 2 minus 10, so that's minus 8. And then we've got minus, now for this determinant, we've got 10 minus 5 times 2. So that's 10 plus 10, so that's 20. So that minus 20. And if we expand that out, we're going to get 2 times minus 8 is minus 16, minus 20, so we get minus 36. And I'm going to put a smiley face because it's the same as what we got up there. So we can see that no matter where we expand, and again you can check for yourselves if you do the second row expansion, or in fact the first, second or third column expansions, you will always get the same determinant. You will get minus 36. Once again, there are plenty of further video exercises from ProPrep which look at calculating determinants of 2 by 2 and 3 by 3 matrices. I do recommend checking them out, and remember, if you sign up using the link in the video description, you'll get 30 days completely free. In part 2 of this video, we'll move on to calculating determinants of 4 by 4 matrices and even higher dimensions. And as we'll see, this is where EROs can really help. Thank you everyone for watching. Please do remember to subscribe if you've enjoyed the video, and I'll see you all soon. Take care.